What's up, everybody? In this next video lesson, we're going to talk about a concept known as electronegativity. Now, first of all, what is electronegativity? This first bullet point explains how electronegativity is the ability of an atom to gain and hold onto an electron when bonding with another atom, and that's a key important concept. This is different than ionization energy, which we learned about, which was the amount of energy needed to remove an electron. This happens to be when two atoms are coming close to one another. How likely is one atom to pull on the bonding electrons compared to the other atom? Essentially, it's a strength of hold on those bonded electrons. Unlike ionization energy, which is measured in joules or kilojoules, electronegativity is a unitless value. It has no label. It is a number that starts at 4 at the highest and is 0 at the lowest. Scientists needed a way to judge how likely one element is to pull on bonding electrons, and so they just made up this concept of electronegativity. It's not based in any unit. What they did was assign the smallest element that could create a bond as 4, the highest number on the periodic table, and that happens to be fluorine in the upper right-hand corner of the periodic table. And they also gave the least likely element to hold electrons on the periodic table a score of 0, or an electronegativity value of 0. Now we need to have a conversation about how that atom attracts the electrons from a different element. Well, first of all, they have to come in close contact with one another, so they bump into each other or they brought close to each other. And what happens is that the nucleus of the smaller element is able to get closer to the outermost electrons of another element. And because that nucleus is a positively charged body, it can begin to attract the electrons and pull it away from the other atom. So in other words, size matters in that the smaller the atom, the stronger the electronegativity pull, because it can get closer and grab onto those electrons more strongly. We call that pull from the nucleus to the electrons an electrostatic attraction. Now let's scroll down here to give myself a little bit of space so I can do a little illustration about how this works. Now, let's take, for example, a small element like fluorine. Fluorine has 9 protons in the nucleus, and it is a very small element compared to something like potassium here, which has 4 energy levels of electrons. That's why I have 4 energy level rings, as you can see. So fluorine bumps into potassium, and because its nucleus is so close to the outer edge, it can get in extra close and grab an electron off the outermost ring or the outermost energy level of potassium. And then what it does is then it grabs it and pulls away and removes that electron with the fluorine. But when it does that, because it has more electrons now, it has a -1 charge. And because potassium lost the electron, it is a +1 charge. And those develop what we call an ionic bond. But the fact is that fluorine was small enough to be able to get close enough. And think about this, that 4th energy level electron, potassium's protons are trying to hold on to it. But because fluorine's nucleus could get closer to that energy level than potassium's nucleus, it won out. It pulled the electron away, essentially removing it, causing it to become a -1 charge, leaving potassium as a +1 charge. With this illustration in mind, what size atoms would you expect to have the highest electronegativity? And if you're thinking the smaller the elements, the higher electronegativity, you would be correct. And by contrast then, larger elements would be considered to have low electronegativity. So let's look at a graph of some data and see if that trend indeed is what we observe. If you look at the second period of the periodic table, on the far left-hand side you'll find lithium. Lithium has the lowest electronegativity element in that period, and as you move to the right, increasing the atomic number, the particles get smaller and smaller and smaller, and the smallest element that's not a noble gas, and we'll address that in a second, but the smallest element that's not a noble gas in the second period is fluorine, which is why it has the highest electronegativity. Does this follow in the 3rd energy level or the 3rd period of the periodic table? It most certainly does. Sodium gets smaller and smaller and smaller and smaller until we reach the end, which is chlorine, and that is the smallest of that period. 3rd period, same. Now you see some up and down in the transition metal, and we'll address that here in a second. But as you can see, the highest in each one of the periods are halogens, which makes sense because they're the smallest elements in a particular period. Now let's talk about the comparison between elements in the same group, like the halogens, for example. Fluorine is the smallest element of the halogens, and as we know, elements get bigger going down the group, and as they get bigger, their electronegativities also get smaller. So that makes sense, because going down a group, the electronegativities get smaller and smaller and smaller, because the particles get bigger and bigger and bigger. And so size is inversely related to electronegativity value. So in summary, electronegativity increases as you go to the right on the periodic table across a period, and as you go up, which is where you'll find the smallest elements to the right on a period and up at the top of a group. Now let's talk about some of those discrepancies you see in the pattern, and I want to draw your attention to zinc and cadmium and mercury. Notice that the electronegativities increase and then they drop for a little period of time and then they continue to increase, and that trend follows when you get to cadmium, and then it increases, and it does it again when you get to mercury, and then it kind of turns back up. Now what do all three of these elements have in common? Well, all three of them end as a d10. So in other words, they are filling up a d orbital. This one is 3d10, this one's 4d10, and this one's 5d10. And so when you get to the end of an orbital, what you get is some stability. A full orbital is fairly stable, and fairly stable means that you don't necessarily want to take on any more electrons. And if you don't want to take on any more electrons, then your electronegativity drops in that regard. So as we move on here, we're going to talk about the reasons why you see some of these weird anomalies in the trend of the electronegativity values on the periodic table. But it's important to point out here that fluorine is the highest one because it's the smallest in this period. And it's the smallest of the halogens, which you can see, which are at the top of each of these period lines. Now, a lot of students might have a misconception that fluorine has the highest electronegativity because it has 7 valence electrons, and for some reason it wants more electrons. Well, atoms don't have free will. They don't have choices. They don't really care necessarily whether or not they get an electron or don't get an electron. And so sometimes I hear students say something like, oh, chlorine's got 7 valence electrons. It wants another valence electron. Well, it's more stable if it gets another valence electron, but it doesn't really want another electron. It has to do, or electronegativity has to do with the fact that chlorine's fairly small compared to its neighbors in the same period, but it's a little bit bigger than its neighbor that's directly above it, which is why it has a slightly less electronegativity. So it has nothing to do with an element's desire to gain electrons. Let's take a look at this first little blue box at the top. Why are the noble gases excluded from the electronegativity trends? And it's because noble gases don't create bonds. And if you don't create bonds, you don't collect electrons when you get close to something. If it has a full stable p6 orbital, then it's not going to gain electrons by getting close to anything. And so that's why there are no electronegativity values, as you can see on this little chart for noble gases. Now looking at this next blue box, we mentioned this a little bit on the last slide, but why do you see a dip at zinc and cadmium, and then again in mercury, and then even a little bit for ytterbium here? Well, it has to do with stability. Stability plays a role. Remember, these are all d10 elements that have a full orbital, and they're stable. And regardless of the fact that their size is smaller than the elements to the left of it, stability plays a role, or is a greater factor in determining the electronegativity value of these elements at the end of the D block. So it has to do with stability, not size. Now let's take a look at this next blue box. Why does it take a couple of steps after the dip at the end of the D10 in order to rebound to get higher than it was before? And so if you think about zinc, the next element over is gallium. Now gallium is a p1 electron in the p block. It's the first element of the p block. This is a 4p1. And p1s are unstable because they have one electron in that p orbital, which is not nearly close to full. And so you can see that it goes up a little bit, but you'd think that because it's smaller moving to the right, that maybe that electronegativity would jump super high. But the fact is that it is the biggest of the p block elements, and it's almost like we need to reset the trend here after we hit zinc at this little minimum, and then starting with the p block, we need to then build that trend back up, elements getting smaller and smaller and smaller going across the p block. And so it's still low, but it's getting bigger as you move to the right. Now finally, let's address this last blue box. How does this trend align with ionization energy? If you remember in our discussion with ionization energy, those elements, those alkali metals, actually had the lowest ionization energy of any of the element in that particular period. And as you moved across, the elements got smaller and smaller and smaller, which means that the attraction of the protons to the electrons increased, and it took more energy to remove those electrons moving to the right, which matches the trend of electronegativity. And this seems to make sense, right? Because as the elements get smaller, it takes more energy to remove those electrons. Also, as elements get smaller, they have a greater ability to grab electrons away from another element, and that's the definition of electronegativity. So it makes sense that ionization energy and electronegativity have the same general trend. Moving to the right and moving up, things increase with ionization energy, more energy needed to remove electrons, and it also is a higher electronegativity, which means it's more likely to grab electrons from something due to its small size. But how are they different? Well, there's a slight difference in what happens here right with that D10 electron. Now, D10 electrons are stable, and in ionization energy, stability is represented by a spike in ionization energy. Stability meaning it's harder to remove that electron. But what we see with electronegativity is that stability, in this case, shows a drop because they don't want to necessarily take any more electrons on. It is stability that causes it to drop in electronegativity, but it's stability that causes zinc to skyrocket when it comes to ionization energy. Well, I hope this little video lesson on electronegativity helps you understand the concept a little bit more. Thanks for watching.